Hello everyone. Welcome back to part 2 of this week's topic, the macro-micro connection. In the last video, we heavily focused on the equations and understanding of the microscopic origin of pressure, as well as root mean square speed and kinetic energy. In this video, we will cover the different types of and properties of gases, entropy, and the second law of thermodynamics. With that being said, let's begin. From chemistry, monatomic gases are individual atoms that are not molecularly bonded with any other atoms. These are usually the noble gases, which are on the farthest right side of the periodic table because they don't have any available valence electrons to be bonded to other valence electrons from other atoms. Some examples are helium and neon. On the other hand, diatomic gases are a pair of atoms bonded together by sharing valence electrons. Some examples are nitrogen and hydrogen gas. It can be noted by the symbol because they have a subscript of 2, meaning there are 2 atoms total. Since monatomic gases are single atoms, they have no potential to rotate. Instead, they can only translate in the x, y, and z directions. For formality, the thermal energy of a system is equal to the summation of the microscopic kinetic and potential energies of the gas molecules. Because monatomic gases do not carry any potential energy, the thermal energy simply reduces down to being equal to translational kinetic energy. Remember, the thermal energy equation can be represented in 2 ways as shown. Capital N is the number of gas molecules in the system, whereas lowercase n is the number of moles of the gas. When we talked about the ideal gas law a few weeks ago, we determined the equation for the change in thermal energy to be the one highlighted in blue. But it was not specified what value the molar specific heat at constant volume, or CV, actually was. Well, CV is based on each circumstance. For a monatomic gas, CV is always equal to 3/2 times R, or 12.5 joules per mole Kelvin, as shown here. Diatomic gases are a bit more complex in that they have 8 degrees of freedom. To break things down, there's 3 degrees of freedom are translational motion in the x, y, and z directions. 3 more degrees of freedom are rotational motion around the x, y, and z axes, and 2 degrees of freedom deal with vibration of the molecules. Although we don't have to know about every little detail about diatomic gases, we just need to know that they have their own equation for thermal energy and value for molar specific heat at constant volume, which are shown here. And this is just a table that came from the textbook just for reference. It also has a system for an elemental solid as well, but in this class we'll primarily be focused on the monatomic and diatomic gases as the systems. Moving forward, we can continue with thermodynamics. The topic of thermodynamics can be broken down into 2 main processes, reversible and irreversible. Reversible processes are just as how they sound. When I have a system in its initial state and it undergoes some process to reach a final state, the system is able to return to its initial state. An example of a reversible process is expanding and compressing a fluid in a turbine. For an irreversible processes, they only can go from an initial to final state, but not back. These processes almost always happen in nature. For example, I hold a ball from a specific height and drop it. It is an irreversible process because gravitational forces only push the ball to the ground, but the ball itself cannot naturally levitate back up to its initial height because it's physically impossible. For reversible processes, they are either theoretical or man-made and must occur under ideal conditions. On the other hand, for irreversible processes, they typically happen in nature. Irreversible processes also increases the entropy of the system. Although we have not talked about entropy, let us segue into this topic. Entropy is essentially the probability that a macroscopic state will occur, which happens spontaneously. Loosely speaking, it is also defined as a measure of the disorder of a system. From the image on the right, the top box has an organized lattice structure where all the molecules are evenly spaced out. This is typically what we see in solids, and they have very low entropy or disorder. As we move down to the bottom box, the molecules are more representative of gas molecules because there is more randomness and scatter, meaning that there is greater entropy overall. Now that we have an idea of what entropy is, we can talk about the second law of thermodynamics, which states that the total entropy of an isolated system never decreases over time, but in actuality, it increases or remains the same. The entropy will remain the same is a special case only when the process is reversible. Another perspective of understanding this law is to note that heat energy will always transfer spontaneously from the hotter system to the cooler system. This was hinted earlier in the topic of calorimetry, but will be quintessential next week when we will be discussing about heat engines and refrigerators. That wraps up with Chapter 20, Micro and Macro Connection. Hopefully this was helpful to you in understanding some of the concepts from gases to entropy to the second law of thermodynamics. If you have any questions, please leave a comment down below or stop by our SI office hours next week. Our times will be in the description link down below. Hope you all have a great weekend and take care.